All right, today we're going to discuss the last three tests in the non-parametric family. So in the previous class, we started to talk about what non-parametrics are, and the idea was that when your data is weirdly distributed, and by weird we mean anything except normal, right? Statisticians believe that any distribution that does not look normal is weird. So if your data are normally distributed, samples or their differences, whatever it is you're dealing with, independent samples or matched pairs, or your data are ordinal, then you cannot really use the concept of the mean. So therefore, we cannot use parameters in our hypothesis testing. That's why we decided not to even try to use parameters. And that's why these methods are called non-parametric. We don't use the mean, we avoid using parameters, so therefore we have to use something else. And we decided to use the idea, the notion of the population distribution location. It's very vague and non-specific. It basically refers to where the majority of data are located on the horizontal axis, right? And also how it is distributed. Is it bimodal, trimodal? Where are the data concentrated? So out of the non-parametric tests in the previous lecture, we have discussed actually two of them, right? So let's take a look. That was primarily concerned with comparing two populations, right? The two tests. We said that if the data are interval and they are independent samples, two populations, comparing two populations, data are interval, and they're independent samples, and at least one of them is not normally distributed, then we're using something that's called Wilcoxon test, sometimes also called Wilcoxon rank sum test. If data are matched pairs, and your differences between matching observations are not normal, then we're using something that's called Wilcoxon signed rank sum test. And these two tests that we looked at yesterday. Okay? So today we're going to look at another test that refers to comparing two populations. What if your data are ordinal? Okay? So we're going to look at sign test, first thing, and that applies. This test is valid only when your data are ordinal and there are matched pairs. So let's go back to slides. So this slide basically summarizes what I just said. Sign test happens when you're comparing two populations. Your data are matched pairs, and they are ordinal. So it applies only when you have ordinal data. Okay, non-numerical, ordinal. But it's the same idea. We're testing same hypothesis. Location is equal, not equal, to the right, to the left, whatever happens from the context of the problem. So let's take a look at the specific example, car ratings. 25 people were asked to ride in a European car, and rank the ride, and after that ride in the North American car, and then rank your ride. How comfortable is that? So who can do that kind of research? Well, there are a lot of car journals, right? Or consumer, rating organizations. They rank different products. So let's say, for example, a car journal would like to perform the study. Are people viewing European cars to be more comfortable compared to American luxury cars or not? So that's the idea, basically. We take 25 people, they ride in an American luxury car and the European luxury car, and after that they say, what do they think about the, how smooth was the ride? Was it bumpy or like suspension, right, essentially? How is it working? Nicely or not? Level of noise, can you hear the noise from outside, or is it muffled? Largely, are the seats comfortable? The seat belts, they're nicely positioned, they don't dig into your neck or something like that, right? A lot of different things. So people say one of these five things, right? Ride was very uncomfortable, didn't like it at all. Quite uncomfortable, that means, well, it was not horrible, but still pretty bad. 3 is neutral, so. 4 is good, and 5 is great, okay? Now, let's take a look at the data. So let's go back to the Scholar, and here is the file, cars.jump. Let's open up the file. In jump, there it is. Okay. All right, so I have two samples, people rating the European car and people rating the American car. So if I want to, again, be formal about that, I have to start in my analysis flow chart with comparing two populations, right? And data type, obviously ordinal, right? 1, 2, 3, 4, 5 are not numbers, they're actually ratings, and they are ordered. 1 is worst, 5 is best. Experimental design, what do you think? Do we deal with independent samples or matched pairs? Well, that depends on how the data were collected, right? So let's see. 25 people were asked to ride in the European car, and then after that, in the North American car, and rank what they think about this matched pairs, right? What makes them matched? Same people, right? My idea of what's a comfortable ride can be different from Christian's idea, right? So therefore, if they take 25 and 25 different people, that can be a factor of study, right? One group is more demanding, right? So therefore, they tend to rank the comfort level lower in general, right? That can get into the mixture. But if every person has their own preferences, right, and biases. But if I'm biased equally for the American car and for the European car, right? And that would be reflected in both of my ratings, right? If I tend to downgrade the ride because I have high standards, that would be included in both ratings, right? So now we're looking at only the difference between European versus American and not the individual differences because it's the same person who is rating the ride. So therefore, going back to the flow chart, I'm dealing with matched pairs, and therefore it's a sign test. Okay. Now, can we conclude at 5% significance that the European car is perceived to be more comfortable than Northern American car? So what I'm saying really here is that my alternative hypothesis, H1, right, is going to be that the location, more comfortable means that it gets high ratings, agree? Closer to 4s and 5s, and not so many 1s and 2s, right? So my alternative is going to be that the location of the European is higher, right? Is greater or to the right. Okay, from the location of American car. That's in statistical language what it means to say that European cars are perceived by customers to be more comfortable, right? And of course, my null, just like it always is that locations, right? I'm going to write it out like that. The locations of both populations, European and American, are the same, right? Are the same. That's what I'm testing. Okay? All right. Now let's go ahead and do the test. These couple of slides pretty much go through the same stuff, right? The location of European is to the right. Okay, and now let's do the actual test. So let's go back to the file. Now, because samples are matched pairs, I don't have to stack them, right? I can just go ahead and use the analysis tool with samples the way they are. All right, so analyze menu, specialized modeling, and I have to use the matched pairs. I used that before, right? When I used the matched pairs t-test, I used the same menu. Okay, so matched observations. Now, note one thing, that even though my data are ordinal, I still label them as numerical, right? Because essentially it doesn't matter. If it's ordinal or numerical, the analysis is done, the test itself is done in the same way. So on the back of my mind, I know that the data are ordinal, but that doesn't really matter. It's going to use numbers and perform the test, okay? So both European and American. Actually, you know what? Let's change the order. Remember how the test is done? eventually it compares your second selection with the first selection, right? The way how I recorded my hypothesis was European was greater, higher ranked as American, right? So European goes first in my hypothesis, so therefore I should pick it second, right? So American should go first in my selection, and European should go second. And when I click OK, you can see that it reversed the selection, right? So I selected American first, European second, but it calculates the difference second minus the first. So it compares European minus American with 0, essentially, right? That's what it does. Okay, and right here what I see essentially is the result of the t-test, right? So by default, when I run the jump test for matched pairs, it gives me the t-test assuming that I'm using the t-test if the sample differences are normally distributed. But that's not it, right? I really want to see the sign test, okay? So sign test, I have to pick it up from the menu, from the right triangle menu. So here's the sign test. Let's go ahead and pick it up, and there it is, okay? And I'm looking at what tail, right tail or the left tail? The right tail, okay? Because I'm thinking that European is higher ranked than American, therefore the difference between them should in general be greater than 0, right? Difference between two distributions in general should be higher than 0. So therefore I'm looking at this p-value, probability greater than m, whatever m is. It's like test statistic that the software calculates behind the scenes, right? So that's my p-value, 0.0053. So what do I do with this p-value? I reject the null, right? And therefore, between this null and the alternative, I reject the null in favor of alternative. And alternative says that European cars, in fact, are statistically higher ranked than American cars, right? Based on these rankings from people with limited sample, we do have a confirmation that European cars are perceived to be more comfortable, subjectively, of course, right? All of that is subjective measurements. Chen?
Can we go back to the
Sure.
sign test results?
Uh-huh.
It's given in terms of greater than or lesser than equal to, which would be the null statement, not the alternative.
Yeah. Equal sign, right?
So, are we reading it correctly?
Well, they probably, what I'm guessing is, look at that one, for example, right? That's a t-test. T-test says greater than, less than, so that's purely, right? But here, what confuses you is equal sign, right? It looks a lot like what we're testing in the null. That's probably a typo, I'm guessing. What they meant is greater than, less than, and greater than or equal. Plus, remember when we discussed that p-value is probability in the tail of the continuous distribution, right? If you include one value or if you exclude one value, it doesn't make a splash numerically, right? So it's really how it looks right on the screen. That's what it is. But in actuality, if you exclude one value or include, p-value stays the same. Okay. So if it's greater than or equal to, wouldn't make a difference computationally. Okay. All right. So this was sign test. Fairly straightforward, right? Okay. Let's keep going. And let's talk about Kruskalwallis test. Kruskalwallis test is essentially an analog in the non-parametric world of our good old friend one-way ANOVA. Remember we discussed one-way ANOVA, and in one-way ANOVA, let me make a new page. Here is what we're testing. Okay, one-way ANOVA is about comparing the means of multiple populations simultaneously, right? So say, for example, I have 5 populations and 5 samples, therefore, coming from them, right? And I want to compare them in one quick test. That would be ANOVA. I'm always testing this hypothesis that the means are the same, mu4 and mu5. And my alternative is always going to be that at least 2 populations are different, right? At least 2 means, at least 2 mu's are different. Okay, so that's my standard test in ANOVA. Well, if you remember, when we discussed ANOVA, we said one of the requirements for the ANOVA test to be useful and valid is every single sample has to be normal, right? And that's one-way ANOVA. One-way ANOVA means that the samples are collected independently, right? I take 5 populations, I have 5 random samples from them, there is nothing that links them together, samples are independent, then I have one-way ANOVA. Every sample must display normality. That was the requirement that we checked, okay? Well, that pretty much brings up the question, well, what if you check samples, 5 of them, for example, and all 5 are non-normal, or 2 are normal and 3 are not, or 1 is not normal and 4 are normal, okay? Then that means that normality is violated. So therefore, ANOVA cannot be really used because, again, when we're talking about non-normal data, something like that, okay, bimodally distributed, for example, right? You don't really know what mean means anymore because here is the mean, but there is not a lot of data looking like that. Here is another candidate for the mean. Here is another candidate for the mean, right? So mean is all over the place. Where is the center of the data? I don't know. Data is just too spread to the right and to the left. I can't really characterize the data with one number and say, yeah, that's a great candidate. It gives you a fair representation of this distribution. So therefore, if one of our samples, let's say sample number 4 is non-normal, then yeah, I'm fine with the rest of the samples, right? How about sample number 4? That's a big question mark, right? What do I mean by the average of the sample number 4? There is no such thing. So therefore, if one of my samples does not pass the normality test, I have to use a non-parametric analog of one-way ANOVA, and that is called Kruskalwallis test. Okay, so let's go back. The Kruskalwallis test applies when you have independently collected samples, just like one-way ANOVA. Requires samples to be independent, not blocked. Okay, and also it can be used in both cases when you have ordinal data, or you have interval data where at least one of the samples proves to be non-normally distributed. Okay, so you check normality, one sample is out of whack, or 2 samples, or all of them, then you can't use ANOVA, you have to use Kruskalwallis. And just like when using ANOVA, we're always testing this hypothesis, right? Means are the same versus no, at least 2 are different. By analogy, pretty much. We test the same hypothesis when using Kruskalwallis. The only difference is we replace the word average, the mean, with the word location, right? That's it. So here is my null. The locations of all k populations are the same. That's analog to my good old statement mu1 equals to mu2 equals to mu3, etc. And at least 2 populations are different in their locations. Other than that, it's a straightforward analog of one-way ANOVA. Okay? So let's do the human resource management problem. Customer ratings of employees in a fast food restaurant. Okay? So here is the problem. Suppose I'm a manager of the fast food restaurant. Okay? 24 hours restaurant. Is McDonald's 24 hours? Some of them. Okay. So let's say I'm managing one of these 24-hour restaurants. So that means that I'm managing every day 3 shifts, right? So let's say I have a 4 p.m. till midnight shift, midnight till 8 in the morning shift, and 8 in the morning till 4 in the afternoon shift. Now, what I want as a manager probably is consistent customer service, right? Doesn't matter what time of the day, customers should receive same service, same response from my employees. So here's what I do. I pick a number of people, visitors to the restaurant, and I tell them, can you please fill out a quick survey? Okay, several questions, literally. And one of the questions says, please rank your overall experience at this location with our employees. Was the service quick? Was everybody polite to you? Did you get what you wanted? Did you have to wait a long time or not? So overall, what was your experience? On the scale from 1 to 4. 1 being bad, poor, and then 2 is fair, okay, 3 is good, and 4 is excellent. So, let's take a look at the data. I'm going to close all things that I don't need. Recording, that's good. Okay. So these are the things that I don't need. And let's take a look at the file, shifts. Let's show. So let's download the file right there. And let's open it up. Here's my file. So I don't have a lot of data, right, to begin with. Every sample is fairly small. It only has 10 observations, right? So here are 10 customers that rated my service from 4 p.m. to midnight, from midnight to 8 a.m., 8 a.m. to 4 in the afternoon. Okay, so as you can see, ratings are different, right? Some say it's excellent, some say good. Is there bad evaluation somewhere here? Yep, there is a poor, and there is fair. So most of them, I believe, are good and excellent, but I do have some bad experiences, right? Okay, but I'm looking at overall, right? Do I have consistent service throughout shift 1, shift 2, and shift 3, right? So let's be formal about that again. Let's use our magical flow chart, okay? Clearly, I'm dealing with 3 different samples, right? So therefore, I have to start over here, comparing 3 or more populations. Data type, obviously ordinal, right? Okay, and after that it says, what's your experimental design? Are you dealing with independently collected samples, or are they blocks? In other words, observations on the same line are linked somehow, right? They form matched set, okay, or block. Well, what do you think? Independent, right? Because here 10 customers from shift 1, here's 10 customers from shift 2, and here's 10 customers from shift 3, right? What would make these observations blocked? Let's say that I want them to be blocked. What would I do? What's the most obvious thing? It should be same person, right? Same person, they come in during one shift, during second shift and third shift. That would make same person evaluate how is it going on 3 shifts. But that would be a weird guy, right? He goes to McDonald's 3 times, including between 12 and 8 in the morning, right? So obviously I can't do that, right? So these are 3 different sets of customers. So independently collected samples. Let me go back to my magical flow chart. So ordinal data, independent samples, bam, Kruskalwallis test, okay? So what exactly am I testing? Well, let me write that down. So in this case, my null hypothesis is that locations, let me call it shift 1, 2, and 3, okay? Of shift 1, 2, and 3 are the same. In other words, distributions of answers are very similar to each other, right? And I don't have really any problem with customer service because it's consistent, okay? Throughout 3 shifts. And my alternative is going to be that at least 2 shifts, AT&T, right? At least 2 shifts differ in terms of their distributions, right? In distributions of answers. Okay? That's what I'm testing. All right, so let's go back. Where's my, here's my file. Now, remember what we do for independently collected data? We have to stack the samples, right? Yeah, so let me go ahead and go to the tables, stack, okay? And I'm staking these 3 shifts right there, and let me rename the columns, right? So I'm going to get 2 columns, one with actual data, another is which shift it came from, right? So the data I'm going to call ratings, and the label for the data I'm going to call shifts. And when I click OK, there it is. All right. Now, here is what I'm going to do. I'm going to use fit y by x. Same tool as I did before. When I used the t-test for independently collected samples, and when I used the Wilcoxon test for independently collected samples of ordinal or interval non-normal data. So same thing, okay? So here I'm studying the effect of shifts. That's my factor of study, right? Essentially, what the question I'm asking is the shift during the day affecting the responses, right? So my factor of study is shift 1, 2, and 3, and what I'm measuring is customers' ratings, right? So that's my numerical measure, 1, 2, 3, or 4. So responses, ratings, and the factor of study is shifts. When I click OK, it actually gives me the scatter plot, but that's not informative, right? It basically says that they're all the same, okay? Now, obviously on different shifts, I had some replicating responses, right? So for example, if I can go back, my original data, in shift number 1, I had good, good, and good, good, four times, right? This shift was measured as good, okay? So these 4 observations are stacked right here. So it's like 4 points, one on the top of another, and I can distinguish them. So it's pretty much non-informative what I see, right? Because multiple points are stacked in all responses, okay? So what I need to do really is go into the analysis right here, okay? And ask for, let's see, non-parametric test. Now, when I'm asking for Wilcoxon, let's try that, Wilcoxon, okay? So it's as if I'm asking for a 2-sample analysis, right? Because Wilcoxon applies when you have 2-sample analysis. But in actuality, it gives me also Kruskalwallis test, okay? So that's pretty much, I believe it's a little bit of a downside of JUMP. It does not give you, so my communications with JUMP, I emailed them about this and they said, well, JUMP will dynamically determine how many levels of factor of study you have, and it will pick either Wilcoxon if you have only 2 different samples, okay? Or it will pick Kruskalwallis if you have 3 or more samples. So in other words, depending on how many columns of data you had originally, it will dynamically pick the right test, Wilcoxon or Kruskalwallis. So in my case, it will pick Kruskalwallis, okay? Because it has 3 different shifts, and JUMP understands that we're dealing with 3 different columns, so therefore it got to be Kruskalwallis, okay? But remember how the test is done? We kind of discussed that. The test is done by arranging the numbers, right? And giving the numbers ratings, correct? So in each column, really what I'm computing is sum of the ranks. And then I'm saying if some of the ranks are about the same, then my samples are approximately same distributed, right? If some of the ranks are going to be differing a lot, then I'm dealing with really populations which are differently distributed, right? So let's take a look. I have scores, right? Each sample contains 10 observations. Well, we know that, okay? Expected score, that means what would you see if the samples are exactly similarly distributed, right? So if they're similarly distributed, then each sample will have sum of the ranks 155, 155, and 155, right? What happens in actuality is one of our shifts has the sum of 169.5 and others 149 and 146.5. So the question is, of course, these sums, are they close enough sufficiently, or are they too away from each other, right? To claim the difference. And that is done by the chi-squared, right? So here is my p-value essentially, chi-squared. So it uses the approximation, okay? That's not an exact test. It uses an approximation. It says, well, hey, our statistic, whatever it is we're computing, is approximately chi-squared distributed. So let's use chi-squared approximation. And that's the p-value. probability in the right tail of the chi-squared distribution that they use as an approximation. 0.78. So what do you think? Do I keep the null or do I reject the null? I keep the null, of course, right? It's a very high p-value, so therefore I keep the null. Oops, I do not reject it in favor of alternative. So, as a manager of this fast food location, do I have a problem with service consistency? No, doesn't look that way, right? Statistically, all of my customer responses in 3 different shifts are similarly distributed. So therefore, I'm running consistent service. So at least on that side of the managing the location, the restaurant, I'm doing fine, right? Different question, am I happy with ratings? Maybe yes, maybe no. But at least I'm consistent, right? Among the 3 shifts. Make sense? Okay, good. All right, so, and all these steps really are described here, okay? So Kruskalwallis test, and here's the p-value, so it's all part of the slides. All right, now, ladies and gentlemen, let's go back briefly. So this is something that I wanted to mention, okay? We're not going to go over this test. Look at that. In this problem, what I did is I compared 3 populations, data type was ordinal, and my experimental design was independent sample, so therefore I used Kruskalwallis test, which is a non-parametric analog of one-way ANOVA. But we also studied two-way ANOVA, right? Two-way ANOVA we're using when our samples are not independent, right? When observations on the same line are matched to one another using some criterion, whatever it is. It can be the same person, it can be the same age of people, you know, in different samples. It can be the same weight. Remember, we did, I believe, cholesterol, effectiveness of cholesterol drug, right, based on age and weight. Age and weight can affect, you know, how effective is the drug. So if we're matching people by the age and weight and give them different drugs, 1, 2, 3, 4, then we're talking about a blocked observation, right? So there is an analog of the two-way ANOVA in the non-parametric family of tests, and that's called Friedman test. So if your experimental design is not independent samples but blocks, then we have to use Friedman test, okay? I just wanted to mention Friedman test. We're not going to do that, partly because JUMP does not have a Friedman test built in, okay? So they simply don't have this test, so therefore this one we're going to skip. But I just wanted to mention to you that it's pretty much the same test. We're testing all the levels, all the locations are the same for all populations, or are they different? At least 2 are different. Same hypothesis we're testing, okay? But it's done using the different test, Friedman test. So that's as far as we're going to go with Friedman test, okay? Finally, the last piece of the puzzle. This is the last test that we're going to study in this course. So that's it. Okay, Spearman correlation test. When is it useful? Sometimes, well, let me actually start with simple linear regression. Remember when we discussed simple linear regression, we started our discussion with correlation coefficient. We said simple linear regression is really about relationship between variable x and some other variable y, and we used interval variables, numerical variables for both x and y. In class we discussed an example where you predict a price of the car based on the mileage of the car, right? Price is continuous variable and the mileage is continuous variable. So we can easily compute coefficient of correlation for 2 continuous variables, okay? Basically it tells you how strongly these variables are linked with each other, right? One variable changes, what kind of effect can we expect in the response variable? If the mileage goes up by 1,000 miles, what happens with the price? Okay, price goes down by how much? That all is measured by the correlation coefficient, okay? How strongly 2 variables are related. Well, what happens if you're dealing with non-interval variables? At least one of them. For example, happiness versus money. That's an interesting study, right? What makes people happy? Well, one of the possible answers is money, right? The more money you have, the happier you are, right? So we can ask ourselves a question, right? Is that true that money is strongly correlated with happiness? So we can conduct the analysis pretty much, right? We can go out, sociological analysis essentially, right? We can go out and get 1,000 people and ask them, how much money are you making? Give us a number. And also on a scale from 1 to 10, tell us how happy you are with life in general, right? So in this case, our X variable will be money, right? How much money they're making, and the response will be happiness. Okay. Now, the salary, the money, is continuous variable, right? It's measured in dollars and cents. How about the level of happiness that they report on the scale from 1 to 10? That's an ordinal data, right? And we can't really compute the coefficient of correlation in this case. Okay. Why? Because large part of this of the reason for that is ordinal data is fairly random. Okay, because I call the categories 1 through 10 because I like to assign them these numbers 1 through 10, right? I could as well call them 10 through 100, 10, 20, 30, etc. instead of 1, 2, 3, 4, right? And that will change the computations, of course, right? Numerically, it will create for me a different correlation coefficient. So therefore, the randomness in how I assign numbers, numerical labels to my categories creates this awkward situation. I assign them one way, it's coefficient of correlation number 1. I assign them differently, it changes everything, okay? So therefore, really, the traditional coefficient of correlation that we looked at doesn't apply anymore, okay? So therefore, we have to come up with something else. And statisticians actually came up with, with something that's called Spearman rank correlation coefficient. So the idea basically is that Spearman coefficient of correlation is computed not based on the numerical values that you have, but rather on their ranks again, right? So we have variable x and variable y. We align all of the x's from smallest to highest and we rank them. We align all of the y's from lowest to highest and we rank them also. And now we're actually computing the coefficient of correlation not between the original numbers, x and y, but between the ranks of numbers x and ranks of numbers y. That's why this technique is called Spearman rank correlation coefficient. Not just simply correlation coefficient, but rank. Okay, we're correlating ranks of x's and ranks of y's. Okay, so to distinguish the Spearman coefficient from the traditional correlation coefficient, we give it a subscript r. Okay. Other than that, it basically has the same interpretation as what we had before. Spearman correlation coefficient is anywhere between +1 and -1. We discussed it, right? The actual correlation coefficient, the original one that we discussed, is a number between -1 and +1. -1 is perfect negative relationship, +1 is perfect positive relationship. 0 is no relationship at all. It's non-existent correlation, right? Same applies to Spearman. It ranges from -1 to +1. -1 or +1 is the best. 0 is the worst. And we have the same informal way to classify them, right? The closer you are to +1 or -1, if you're above 0.7 or below -0.7, we call it strong correlation. If you're between 0.3 and 0.7, we call it moderate. If you're close to 0, between -0.3 and +0.3, we call it weak correlation, right? Same thing applies. And in this case, actually, here's what we run. Okay, when we say, is happiness related to money? We need to compute the correlation coefficient. But it can be fairly small, right? It can be like +0.3, for example. Then in this case, we can say, well, is that an accidental correlation? Because it can be just, by random choice of sample, we got this value. You pick a different sample, it swings to -0.25, in which case you will say, wow, some of them are positive, some are negative. Probably I'm talking about no correlation at all, because it's too much randomness from sample to sample, okay? So here's what we test in the Spearman correlation coefficient. Our null hypothesis is going to be that x and y are not related at all, statistically. So whatever we get from the computations can be replaced with 0, and that would be just as good of a correlation, okay? An alternative would be that no, statistically, what you're observing in your sample, Spearman rank correlation, is significant, cannot be replaced with 0. So that's the only test that we're going to perform. Okay? All right. Now let's take a look at the problem. Okay? Here is the problem that I came up with years ago. IDEAs. I got to tell you that at CNU, IDEAs are used universally for the professor's evaluations. So remember we discussed today that professors are evaluated just like students, right? Our performance every year is evaluated. How our teaching is evaluated is when you fill out the IDEAs, we get the scores back, okay? The scores can be good, in the middle, or bad. So the idea basically is professors have to provide good scores or excellent scores. If the scores are bad, that's something that you can improve, right? Something that you can work on. So some professors actually at CNU are against that system. They say that it's too numerical. It does not take into account, like for example, what students think about professor. Some professors may say, well, we also would like to be evaluated by our colleagues who come into the classes, sit and observe, and they can make a more informed judgment how rigorous your course is, how well you present the material, so it should be a more comprehensive system. And let's say that some professors believe that what students say on the IDEAs at the end of the semester is highly influenced by what grade they expect. In other words, the idea behind that is, let's say I'm an average student or bad student, okay? So I was slacking off this semester. I was missing classes, didn't submit my homework, got bad grades didn't study, bad grades on exams, etc., etc. So as the semester is getting to its close, I'm thinking, oh man, I'm going to get a bad grade. So how about I take it out on the professor? I'm going to give them bad evaluations because I expect my grade to be not so high. So some professors may believe that students' evaluations of the class are based on the not on the rigor of the class, but rather on what they expect to get. If I'm expecting to get an A, I'll give professor good evaluations. If I'm expecting to get a D, I'm going to give them bad evaluations. Can that be the case? Well, it may, right, or may not. We have to collect the data. So here's what was done, okay? We asked number of students and 2 questions, right? And then after that, all of that was recorded. How would you rate this class? On the scale from 1 through 5. 1 poor, fair, 3 good, very good, and excellent. And also, what grade do you expect, based on your performance in class so far, to be your final grade? Okay, if it's F, failing class, it's a 1. If it's an A, that's a 5. Everything else is in between. So, question is there enough evidence in the sample to conclude that this theory is correct? That the lower the grade, the lower the evaluations, right? Another way around. The higher the grade expectation, the better the grade, the course evaluations. Okay, let's see. This data set, by the way, is completely made up. So whatever results we're going to end up with, take them with a grain of salt. Okay, that's just pedagogical problem, but nothing more than that. Not a research. So class grades. I'm going to download the file, and let me close the stuff that I don't need anymore. Nope. And that one as well. And now let's open up the class grades. Okay. There it is. So, how many students did we have in our sample? Looks like a lot. 125 people, right? That was my sample size. And you can see that first person, for example, said they rank the class as very good, but strangely enough, they're going to expect a D in the class, right? You don't see that a lot, probably. Another said that this class is good, and they expect a C. Another said very good, they expect F. Wow, that's weird, right? That's not what we expect at all. Okay, anyhow, let's be formal about that again, right? Statistics is a toolbox with instructions how to use it. So this is our instruction, right? Which tool to use in what situation. So what are we talking about? Describing one population, comparing 2, comparing 3 or more, or are we analyzing relationship? What do you think? where do I begin? I'm really trying to see if the grade expectations drive the class ratings, right? And that falls under the umbrella analyze the relationship between two variables. Agree? So let me focus more on the tree number 4 right here, okay? Analyze relationship between two variables. That's what I have, right? Data type, ordinal, both of them, right? My rankings of the class from 1 through 4 is ordinal, and my grades are ordinal. You realize that grades that you receive at CNU, the letter grades, this is ordinal data actually. And then after that you're computing GPA based on the ordinal data, something that we should never do with ordinal data according to the teachings of this class, right? Ordinal data does not have a mean, right? But we do kind of compute the mean based on ordinal data. That's called GPA, right? Okay, anyhow, I have two samples. It's really one sample, right? One sample that gives me column 1 and column 2. So it's just one sample of students, 2 responses from each student, right? So I'm comparing 2 variables of ordinal data. And the answer for me would be, I need to use Spearman rank correlation test, okay? So just like what we discussed about 5 minutes ago, what exactly am I testing? I'm testing this hypothesis, right? Null is that the correlation, Spearman rank correlation, between expected grade in class and the class evaluation is equal to 0, right? Which means that they have no relationship, right? Whatever students expect to receive has no effect on how high or low they rank the class. And the alternative would be that no, the Spearman rank correlation is statistically non-zero. This is what I'm testing, okay? And the test actually is performed, it's very easy to do that in JUMP. So let's go back. Remember, Leshu, some time ago when we talked about the multiple linear regression, we discussed multi-collinearity, right? And how we construct the coefficient of correlation matrix for each variable versus each other variable. Let's do the same thing here, okay? So note also that even though my data are ordinal, it's labeled again as numerical, right? So I don't keep the ordinal part, I do that as a numerical, okay? Because essentially what it does is it computes, arranges values from smallest to highest, it gives them the ranks, and then computes the correlation between the ranks, right? So it doesn't really matter if I use ordinal or numerical, okay? So the test is done. While this data is ordinal, I'm still going to treat that as if these were numbers. But I'm going to compute ranks, so numbers wouldn't really matter. Okay, so I'm going to go to Analyze menu and to the multivariate methods and use this option, multivariate. In multivariate, we use to compute the coefficients of correlation, right? So let me go ahead and put both columns, ratings of the class and expected grade, into this area, Y column. And you can see that it says required numerical continuous. That's primarily the reason why, even though the data are ordinal, I label them as numerical. Because the test in JUMP requires them to be formally labeled as numerical, okay? So I'm going to put them both here. And when I click OK, it computes the old good correlation matrix for me, right? So let's take a minute to kind of discuss what is it. So if the data were numerical, which they're not, then I would have this correlation, right? Ratings with themselves is perfect one. We discussed that, right? Variable with itself is always perfectly correlated, right? So therefore, we're not going to look at these diagonal portions. This 1.0 and 1.0, I'm going to discard them. All right, so if I would treat the variables as continuous, then ratings with grades are going to be correlated, well, again, informally by judging, the size of this correlation ellipse. I'd say it's not a very high correlation, right? Because ellipse, if it's looking like a circle, that's bad, right? It should look like a more or less straight line, so it should be very narrow. Then I have a good correlation. So by judging by the size of this ellipse, I'd say not a huge correlation, right? And that actually is confirmed right here, okay? I have ratings correlated with grade expectations minus 0.3, negative correlation. Okay, and 0.3 is pretty weak, right? We discussed that. 0.3 or minus 0.3 is weak, right? Okay, but that's not a legitimate thing to do right now because my numbers, these are not really numbers, right? That I'm talking about. These are categories. I just labeled them 1, 2, 3, 4, 5. Okay? So I have to go back and test the hypothesis on the Spearman correlation coefficient, right? So let's go ahead and go to the red triangle. Everything is in red triangle menu, right? Okay. So can you guess which option I need to pick? Non-parametric correlations right there, right? And you can see that actually JUMP can do 3 different things for us, right? We're going to discuss only this one, right? Spearman correlation, then there is Kendall, and there is, oh my god, how do you pronounce that? Hovding, right? Hovding's correlation. All right, so we're going to use the Spearman option. Okay, so you can see that JUMP actually did a couple of things, right? Number one, it computed the correlation, Spearman correlation coefficient by itself, minus 0.26. And you can see that it's actually fairly close to my original correlation coefficient, right? That I cannot use really, this minus 0.3, right? Because it computes the correlation between ordinal numbers, which is not a legitimate thing to do, okay? But Spearman, anyway, turned out to be fairly close, minus 0.26, okay? So I'm going to go back and say, oops, where is that? Right here. That my Spearman correlation coefficient is minus 0.26, which is pretty weak, right? That is fairly close. It's between minus 0.3 and plus 0.3, right? So therefore, I'd say the correlation is weak, but is it statistically significant, right? And here's my p-value. It says probability of greater than the statistics, right? Whatever statistics is, okay? 0.0031. That's my p-value for the test. So with p-value 0.0031, what do I do? Of course, I reject the null, right? It's even less than 1%, 0.01. So I reject the null in favor of alternative. And what does my alternative say? That this is a statistically significant correlation. It's not accidental. Okay? So this negative 0.26 Spearman rank correlation coefficient that I computed actually is a sign that they are correlated, but not in the way that I suspected, right? Minus sign tells you what? That it's a reversed relationship, right? Low ratings in general, low grade expectation in general generates high class evaluations. Another way around. If people are, getting high grades, they tend to downgrade the class, right? So what professors believed in this example, right? Let's go back to the example. Professors believe that it's the other way around, right? If your grade expectation is low, then you will downgrade the class, right? Turns out to be, it's actually reversed, according to our data, right? If your grades are low, you tend to grade the class higher. And if your grade expectation is high, you tend to grade the class lower. And that's a statistically significant relationship, okay? Make sense? Well, actually it doesn't, right? But that's what the data tells us. It doesn't make any sense, right? Students who are expected to perform worse, they tend to say good things about class. Well, on the other hand, sometimes, if the class is really rigorous, right? You can kind of make an argument. If the class is really rigorous and really valuable, your performance can be not so good in this class, but you learn a lot, right? So therefore students are saying, yeah, I'm not going to get a good grade, but I learned a lot. So that's a good class. That's valuable for me, okay? Can happen. All right. So ladies and gentlemen, this is the end of all of material that I have for this semester. Do you have any questions, concerns, or complaints? Patrick?
Can you
Okay, let me stop the recording here.